impressions or something which need to get into our mind. That's the impression I mean. Bonding, the crystal structure and macroscopic properties. So now I have covered the entire solid state physics or material science, where we always start with the base of bonding. But I'm talking about macroscopic properties which are very essential for application. And this is what is the connection, where the connection comes and how the connection comes, we will do first. And then attributes or intrinsic properties of electrons and their impact in materials behavior. Spin, I may not do exclusively on spin, but I would be using, and when I do density of states, I will be able to tell you how you get the fractional magnetic moment. So that is a view we need to have, and spin polarization, spin polarized calculations are taking up, and therefore that plays an important role, especially when you deal with novel advanced materials in research. Then the reciprocal lattice and Brillouin zone, that is the most important thing for the experimentalist and also for the theoreticians, because we are doing everything in that first Brillouin zone. So what is the significance of that first Brillouin zone is a very important thing which we need to understand to proceed. Fine. Now, let's do the conceptual frame to optimize the solid state theories for materials investigation. So what do I mean by conceptual frame? So when you want to do any theory, a frame of mind, the approach, the way you view it is very, very important. And that's why I call it conceptual frame to optimize the solid state theories for materials investigation. So in the classification of solid, this is just for us to refresh our minds and to know how we deal with the different areas in this subject. I have just given this array, this diagram for us to understand. So in the solids investigation, first, how do you classify the solid in the first place? So when we classify the solid, the first classification, which is very much familiar to all of us, come from the arrangement, the very arrangement of the atoms, because we know atoms are bound together through some way, way of bonding, that the different types of bonding. So what decides that bonding? So we will be doing it, but I want you to understand, through some bonding, the atoms get bound and the solid is formed. So in that arrangement of atoms forming the solid, you can have crystalline solids and amorphous solid. When there is periodicity in the arrangement of atoms, that is crystalline. So aperiodicity comes, then we call it amorphous. And amorphous solid also, it will have islands of periodicity. So this is fundamentally you try to investigate from the idea of arrangement of atoms, which is the first view of classification of solid. And the second classification comes based on the properties. So you want to investigate different types of solid, you can classify them based on the properties. For example, take the property of magnetism. So it is a very important, one of the salient properties of material. So now, what are magnetic solids? So if the solids respond to external magnetic field, then it is called magnetic solid. So if it doesn't respond to external magnetic field, then it is a non-magnetic one. But even among the magnetic materials, you have different types. Like you can have diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. So these are all the classifications among the magnetic materials. Then you ask a question, in what way one type of magnetism is different from the other? So you can distinguish one from the other based on the interior, that is the phenomena that governs what is known as magnetism. So that's how you can visualize the classification of solid. Another frame of mind could be based on another problem. Say, for example, we just said about magnetism. Take another important property, which is conductivity. So based on conductivity, that is the title under which we can study conductors, semiconductors, and insulators. And most of the time, we simply classify the solids like this, and say conductors. Then we can say the valence band and the conduction band overlap, there is no gap. Semiconductor, there is gap. An insulator, the gap is very wide. And this is how we just have a very simple overall view of the property of conductors, where the valence band and the conduction band overlap, and that gives free electron, and that is the reason for conductivity. But actually speaking, when we try to investigate the properties of various conducting materials, for example, metals, they are good conductors. Semiconductors can also conduct. Superconductors can conduct. Graphene, today two-dimensional graphene can also conduct. But all of them are conductors. They do conduct. But you just look at the phenomena that contributes, and that is responsible for conduction. In these four classified materials, take metals are the familiar conductors for us. These metals have free electrons. Metallic bonding gives free electrons, and these free electrons have got sufficient energy, and they move around the entire solid, and they belong to conduction band. And there is no distinction between valence because they overlap. Valence and conduction bands overlap, and therefore free electrons contribute to very good conduction, and that's why we call conductors or the metals excellent conductors or conductivity side. Now, when you talk about semiconductors, there are no free electrons. Only made free electrons can contribute to conduction in semiconductors. So what do you mean by made free electrons? If you remember the fundamental or the pure semiconductors, say silicon and germanium, remember the picture where the covalent bonding, the 4 electrons, or say for example 4 electrons belonging to one germanium atom getting bounded with 4 other electrons of the 4 near neighbors, then it satisfies after. So where are these electrons which are getting bounded through covalent bonding, sharing of electrons? All of them are shared. So they are in the valence band. So when the electrons are in the valence band, they are tied up. They are bound electrons. They cannot contribute to conduction unless the electrons move in the conduction band. They will not be able to contribute for conduction. Another important thing, there can be a number of electrons in the valence band, but all of them would be bound electrons, and they will not contribute for conduction. So you need to take only the conduction electrons in the conduction band, and remember they will leave holes behind. So conduction in semiconductor is due to electrons in the conduction band, holes in the valence band. So totally electron hole conduction comes in semiconductor. Now what about the superconductor? In superconductor, that's a low temperature phenomena where the 2 electrons are connected or interacting via the medium of phonons. Here they are called the Cooper pairs or super pair electrons. So the super pair electrons are responsible for conduction. The phenomena of conduction is totally different in superconductor. Now coming to two-dimensional material, two-dimensional form of carbon called the graphene. So in two-dimensional graphene, you have only hopping electrons. So the pi bonded electrons hop. So even in this basic thing called conductors, you really want to investigate the phenomena, you will understand the phenomena is different. Though the electrons are responsible for conduction, the way in which they conduct, the phenomena that is responsible for giving conduction in these four materials are totally different. Metals free electrons, semiconductor electron hole, superconductor Cooper electrons, and graphene hopping electrons. But the theories of electrons should be able to accommodate all these features the electrons show in different materials, meaning in different environment. That should be clear in our mind when we investigate sun. Okay, so then another important classification, there are many ways you can look at it, but I'm just giving you different perception for you to think. So now, when you talk about the dimension, you can have bulk, you can have nanomaterials. Now, it is based on the dimension. So if the particle size is less than 100 nanometer, then the material with which, the materials made out of such particles are called nanomaterial. If the particle size is more than 100 nanometer, then they form bulk material. So here again, I want you to understand any dimension, any length can be, anything can be expressed in different units. Anything can be expressed in meter, or in centimeter, or in millimeter, or in nanometer. So we know 10 power minus 9 meters is equal to 1 nanometer. So if you can measure the size of the particle and express it in nanometer form, and if its dimension is, or if the size is less than 100 nanometer, then it is nano. So now for the students' understanding, I just want to say, because we have a heterogeneous audience here, starting with UG to teachers. And so let me just give you some kind of a feeling for the particle size. What is the particle here? Say you take a chalk piece. We write on the blackboard, right? So when you write the chalk piece on the blackboard, then the particles fall down. You take one of the chalk powder, we call chalk powder, take one, if you can take one particle out of this powder, chalk powder, which is fallen while writing, and measure the dimension. If it is less than 100 nanometer, then you can call that chalk piece as nano chalk. There's no nano chalk piece as it is. So I'm just giving you an idea. So this is how the, otherwise if it is a more than 100 nanometer particle size, then it is bulk. So now how this, I'm just giving you idea of bulk and nano, but the theory of nano, quantum confinement, surface effect, all those things have to be understood with solid state fundamental theory perception. So that's why I'm showing you this particular classification. Then let's see the next study of solids. When you analyze solid, or when you investigate, so now I want to tell the student audience especially, now we should not be studying everything as a one derivation after the other, or one portion in the syllabus and there's another for one unit and another unit. There should be a continuity in a thinking process. So in our study of solid or analysis, always aim high. We do something to do research or to do something more than what is given in our curriculum. So that should be the perception which you achieve. So when you study the solids or analyze the solids, you can have two views or two contributions to the property of the solid. One contribution could be the phononic contribution, and another can be the electronic contribution. So if you take the solid, so we are going to discuss briefly some important points and the bonding now, but I want you to visualize. That vision should be clear in your mind. What is a solid? Number of atoms have come together, and you can think the outermost electrons leave the atoms, then the atom will have more positive charge compared to electron because it is deprived of our electron, and therefore You can call it iron core because every single atom forming that particular solid will be having a positive, excess positive nature, and therefore iron core. So suppose I imagine any solid to be having the iron core, or the atomic arrangement, which is called the lattice. So atomic arrangement of any atoms is the lattice. So those of you who have done crystal structure will know there is lattice, there's a basis, and the crystal structure, unit cell, perimeter cell, which I will be touching upon in a few minutes. But I'm just telling you, imagine the atoms have come together forming the solid. Suppose I give heat, what would happen? These lattice, now the lattice usage meaning the arranged atoms, they will start vibrating about the mean position. That's all they can do. Because of the heavy mass, they will respond to any external stimuli just by vibrating. So they can vibrate about the mean position. Again, this vibration is not going to be very uniform like this along X or along Y or along Z lines. It will be having 3-component vibrations about the mean position like this. So when they vibrate, they will be releasing the quantized energy called phonons. So the lattice are always represented with the phonons because their impact will be, or their response will be shown in terms of phonons. So you can have the study what these phonons are doing in this extent. When it gives the heat, what the lattice is doing, how will I know? I just have to see the phonons. And then if I give a field, what would happen, and so on and so forth. Another one, electrons are there. But if they are free electrons, there are free electrons in the solid. These free electrons will have an easy way through the entire solid. Now I'm saying they are free and they have random motion. They can have freedom to move around anywhere in the solid. But when we do higher theories like density functional theory, where we talk about exchange correlations, we say they have correlated motion. But at this stage, when we are still in the very first understanding level of theory, we are going to say they are having a random motion. So when these electrons move through the solid with random nature, then what will they do? When heat is given or field is given, anything is given, how they respond to external stimuli. Now, the way, the very nature of both of them is different. One is just giving oscillation, that is the atomic arrangements or the lattice can give only oscillation about the mean position. But the electrons can have free movement. They are not going to belong to any particular location in the solid. They have freedom of movement. So any theory that you propose, maybe you try to understand the thermal conduction of the solid, electrical conduction of the solid, or anything of the solid, then the theories are proposed to understand that particular property. These theories proposed should first of all take in the mind that the nature of the atomic arrangement or the lattice is different from free electron. So the theory that is adopted, though you explain the same property, say thermal conduction, you should have different methodology or prescription for the lattice and a different prescription for the electrons. And that's the reason we have two different theories of lattice and theories of totally the nature is different, two different ways to accommodate their influence. So this is how you should understand. Okay, so now in the we can think of, so when you try to investigate it, so now when you investigate lattice, what did I say? They can have oscillation or vibration about the mean position. So what is the easiest thing associated or familiar thing associated with the oscillation or vibration? Frequency of oscillation. So if the lattice is going to vibrate in response to the external stimuli, then they will release phonons based on how much they are affected, how much is the oscillation. When the temperature is almost zero, the entropy will totally reduce and there will be almost a peace. They have only 0 point energy. You cannot expect too much of phononic energy. But when you increase the temperature, so temperature within the threshold that vibrations go on, then the vibration, the way they respond, or the magnitude of the stimuli, temperature or whatsoever mean, can be understood by knowing the frequency of vibration. Is it vehement or very mild? That depends on external stimuli. So now, if the vibration is more, the frequency of oscillation will also be more. So, phonons are the lattice outcome, the behavior is visualized. Remember, in solid state physics, you visualize the situation, adopt a theory, and use appropriate mathematics and quantum, get the result, and draw your result and visualize it. You can visualize this frequency of oscillation. So now, they are called phonon frequency bands. And what about electrons? Electrons are randomly moving at this juncture. So we can capitalize them or understand in terms of energy band. So phonon is frequency band because of the inherent nature, and for electrons it is energy band. Fine. Now, that's phonon. Lattice vibration is a quantized energy, I said. Energy is h cross omega. You can write momentum P as a lambda, or in terms of P is equal to h cross k, familiar relationships. And this is what is the frequency band. So if you have done lattice vibrations, monatomic lattice and the diatomic lattice, so phonon dispersion, where it is happening in the first Brillouin zone. See, now you see your y-axis, I've said y, omega, y, frequency is important. So frequency of oscillation, omega, is drawn, is studied, where it runs between minus pi by a and plus pi by a, and the x-axis is the reciprocal lattice vector k. Or rather, it is magnitude of the reciprocal lattice vector k with a wave number. So k value between minus pi by a and plus pi by a is taken. Why only that range of k? Because that's the first Brillouin zone. I will explain why that range is always taken. Anything you investigate only in that range. So first Brillouin zone has got the significance. So why and how that significance come to the first Brillouin zone, I'm going to explain. So now you just take omega versus k. And for a monatomic, meaning only one type of atom that forms the particular solid, and see how it omega, both positive negative values of k, you just have this relationship. Suppose two atoms are forming the lattice, a diatomic, you see optical branch, two branches. See, this is one branch and this is another branch, optical and acoustic. So now, as I have put a note here, this is included just for introducing the solid, not for doing phonons. We are going to concentrate in this series only about the electrons. This series doesn't talk about lattice or the omega versus or phononic modes. If possible, we will do it in another series. But just to know, there is another counterpart for electrons. I'm just showing you this. So if there are p atoms in the perimeter cell, that is minimum volume cell, there will be 3p branches, 3 acoustic branches, always 3p minus 3 optical branches. Suppose p atoms are there in the perimeter cell and there are n perimeter cell, the total number of atoms will be pn. So this is how the calculations are done. And how many branches? So branches mean for a particular k, how many values of omega are possible. I'm reserving it for future series. I'm not going to go in detail. I just want you to know omega versus k is used for studying the lattice, but we are going to use only the electronic band structures or electronic theories. But phonons do influence the properties. You cannot just take them for granted or neglect them. You need to also, when you want to investigate a solid, when you want to do a research in a particular solid, and you want to propose that particular solid for any application, you should be able to understand certain properties. Phonons play a major role. Therefore, you need to know their contribution also. So phonons do influence the properties of materials, of what, like resistance, conductivity, specificity, superconductivity, etc., etc. So now look at this. Electron dispersion. I said for electrons, it is energy of the electron where in the same first Brillouin zone. So now in the first, this is actually the first Brillouin zone which I have taken along the x-axis, but I have given more symmetrical points and the directions. I am going to explain to you what this Brillouin zone is and how you construct briefly in subsequent lectures in the same series. But I want you to know, look at this picture. Electron dispersion in the first Brillouin zone, meaning electrons have the wave character because we are dealing with quantum mechanics. So you can very well visualize, study electrons with the wave picture. So electrons have the wave character, and scattering of electrons gives rise to band structure. So they go around scattering within the solid. So at different, it is happening in the reciprocal space. So you just calculate their energies within the reciprocal space and you draw that, visualize it. What you get is the band structure, which is the plot of energy states of electron in reciprocal space or momentum space, also known as K space. Now, this is the generic nature. I've just taken one of my own very old work, where it is a ternary semiconductor. Why I took this, not to explain band structure, which is too early for me to do now. But I want you to understand, we cannot take the electrons for granted. See, when we study the basic physics, what do we say? Say, for example, you bias. So in biasing, you just say when the biasing is done, the electrons are accelerated and they move towards the positive electrode, and that's how you do. When the magnetic field is applied, you simply say the electrons are acted upon by the magnetic force or the Lorentz force, and they bend, they take a circular path. That's so you group all of them as electrons. Electrons are taking a circular path, electrons are getting deviated by the potential, and the electrons are getting accelerated, and the electrons are drifting in the situation. But you should understand, the individual electrons are important in solid state physics investigation. What are those individual electrons? Remember, when you did atomic physics, you would have done what is known as quantum state. So what is a quantum state? Every single electron will possess one quantum state, meaning a set of quantum numbers. There can be N, L, ML, and MS. So now, there can, Pauli's exclusion principle says that no two electrons can have the same quantum state. So that means every single electron, that's like address of an electron. So when you do research, when you want to do analysis, you should be, especially when you want to have theoretical perception, theoretical conceptual clarity, then you should know in this situation what the S electron is doing. And if the solid is having more than one atom, like the case I have showed, I have just showed A, B, C2. So here I have said A is a cadmium CD, and B is silicon, and C is arsenic. So these are the three atoms that I have chosen. So in this situation, look at the valence electrons, because we know the core electrons do not participate or contribute for any of the properties of the solid, and we give importance only to valence electrons, right? So now three atoms together, they are forming this ternary semiconducting compound, say CdSiAs2. This is the compound. So now I'm not explaining about the compound. I'm just asking you to look at the individual atom that is forming the compound. So now CD. So now it is a transition element. Now what is the outermost are the valence? 4d10, 5s2. And what about silicon? 3s2, 3p2. What about arsenic? 4s2, 4p3. Now, when a particular compound is formed using the three elements combining, forming a semiconductor, ternary semiconductor, then these electrons are going to play a major role. So I said the electrons should be seen as energy in the reciprocal space. Now we are not going to talk about vibration or frequency. We are going to talk in terms of energy. Energy of what? Energy of these valence electrons. Then I should see in this reciprocal space, just take it for granted. The x-axis is the first Brillouin zone, k vectors, now, and then k values, and y-axis energy. This is not a fundamental theory. This is a sophisticated density function theory result. But you just see below zero are bound states, above zero are unbound states, or you can say conduction and valence. But now I need to see where is this D10 electron, because each one of them will have some energy. I said they are individually, they are different. They have their own characteristics. In this particular solid, when I visualize, when I calculate energy, draw the energy and visualize, then D electrons are very much bound, and this corresponds to the D states. And these ranges correspond to the P states of B, S and P, and this of there's a silicon and arsenic. So individual, now you may wonder, what are these lines? See now, if I pinpoint one particular line, which is a corresponding band for a particular electron, as you vary the value in the x-axis, as you move through the various positions in your reciprocal space with the varying k values, it is having different curvatures. It is not flat straight line. So every single electron have varied energy in the reciprocal space. So even if you take S electron, its energy is different from D, P is different from S. They have their own energy, and even that single electron is having varied nature across in the reciprocal space. Now this picture is important for us. Now what is the aim of the series? The aim of the series is to have a good grasp of base which is needed to develop the theories, starting with the fundamental theory to the sophisticated theory, and therefore we will have a better clarity in interpreting our results in research. Now, very quickly, let me just go through this slide just for continuity. And intrinsic properties. So the electrons do have charge, and they have up spin and the down spin, and they have mass. And familiarity while studying or discussing. Charge, we always study, or we are familiar with the usage of charge, the word charge, when we talk about conduction, biasing in the devices. And so the electrons charges, we always say they have negative charge, of course, minus 1.6 in 10 power minus 19. So this is the magnitude. So we always use the terminology charge there only. But when we do magnetism, we talk about up spin and the down spin, and parallel spin, and unbalanced spin, and so on and so forth. only when we do magnetism. But when we do ferromagnetism, you don't talk about the charge. So you just say the spins are are a alignment of spin. That gives some kind of contribution towards understanding ferromagnetism or a domain in a ferromagnetism. But here you never talked about the charge. And again, the mass of the electron is 9.11 into 10 power minus 31 kg. If you remember, in some of the journals, they just quote different masses for the electron. Sometimes the mass of the electron is with the negative sign. So that is called the effective mass. So what do you mean by this effective mass? So this effective mass is the mass experienced by the electron when its free motion is hindered. So this I will explain when I do KP model, but you should understand the mass can be represented differently, but actually its mass is the same. This concept is used to adjust the potential. I'm going to explain to you. So these are the attributes of electrons. We cannot casually take them. Give importance to each of the terms when we use them. Okay. So behavior of electrons do decide the properties of the solid, like cohesive property, electronic, optical, magnetic, superconducting properties, and a few more properties of the solid. So they play a very vital role, and we can even call the electrons to be like the heroes in the solid. They are the ones who play a vital role when it comes to material investigation for application.